Yeah.
Probability always has a lot of terminology that we need to be familiar with, so we need to go through a bunch of that here at the start. So the following terms you need to understand. A trial is the number of times that you conduct an experiment. So for example, the number of times that you roll a dice. An outcome is the results that you get. So from rolling your dice, the outcomes are 1, 2, 3, 4, 5, and 6. An event changes from question to question. It is the desired or favourable result that you want. So if we want an odd number when rolling the die, we would be wanting the numbers 1, 3, or 5. Equally likely outcomes are outcomes that have the same chance of occurring. Example 1 on the outcomes heads and tails, they are equally likely on our coin. Example 2, there are 6 possible outcomes on our dice, 1, 2, 3, 4, 5, and 6. This is a complete list of the possible outcomes because the time the dice is rolled, one and only one of these outcomes will occur. We may thus regard these 6 possible outcomes as equally likely possible outcomes. Randomness. In the context of equally likely possible outcomes, saying that a die is thrown randomly means that we are justified in assigning the same probability to each of the 6 possible outcomes. In a similar way, a card can be drawn at random from a pack, or a queue of people can be formed in a random order. Impossible event. An impossible event, if something cannot happen, it has a probability of 0. A certain or a definite event, if something must happen, then it has a probability of 1 or 100%. Sample space, we give the letter capital S, and is a list of all possible answers inside a set of curled brackets. So for example, the sample space for flipping a coin is S for sample space equals curly brackets, head, comma, tails. Or the sample space for rolling a dice is S for sample space, curly brackets, 1, 2, 3, 4, 5, 6, right? Uniform sample space. A finite sample space is called uniform if one and only one of these outcomes will occur.
What's an example?
You're doing a trial just once, so only one thing is going to happen on that dice. An event space. The set of all favourable outcomes is called the event space. A complement, the complement of an event E, so the event is called E, is the probability that it does not occur. So probability of something not occurring is 1 minus the probability that it does occur, which is often an easier way to calculate things, especially when it comes to tree diagrams. So the formula in the first box there is the one we're most familiar with. Probability of an event equals the number of favourable outcomes over the total number of trials. In the textbook, they have also provided this slightly shortened version. It means the same thing. Those lines are not absolute values. It is to indicate the number of favourable elements. So I think the E is for the favourable elements, and S is for the total number of things in your sample space, your total number of things that you've got. Okay, so here is, you've seen this picture many times before, our pack of playing cards. We know that there are 52 cards in a deck. There are 4 suits, the clubs, hearts, spades and diamonds, and in each one of those suits there is 13 cards. We usually consider from ace up to 10, and then we have our picture cards, sometimes called court cards, either jack, queens and kings. Alright, so from the cards we want to find some probabilities. Question 1. From a pack of 52 playing cards, a card is drawn at random. Find the probability that the card will be the 5 of spades. So the 5 of spades is very specific. It is one specific card out of the whole deck, so it would be a probability of 1 out of 52. Part B, find the probability of getting a jack. So the J's, there are 4 of them out of the 52, and we like to simplify our fractions where we can. So dividing top and bottom by 4, we get 1 out of 13. A black card, I'm sure some of you could go straight to the answer of a half, and that is definitely fine. If you wanted to count them all up though, there are 26 black cards. out of the 52, which simplifies to a half. A diamond, another one that you might be able to go straight to the simplified answer, but remember that there are 13 diamonds in your pack of 52, which is exactly 1/4, because it's 1 out of the 4 suits. Okay? Very happy for you to go straight to 1/4, or for C to go straight to a half. Part E, an even number. So the even numbers are the 2, 4, 6, 8, and 10. So that is 5 in each suit, but there's 4 suits, so 5 times 4 makes 20 cards, or you can count them up one at a time if you want to, but you won't have that diagram in your test. You need to know what that looks like. So 20 out of 52, simplify that down, and you get 5 out of 13. Any card except a 7. So there is 4 sevens. So you could say, if I take off the 4 sevens, that means that there is 48 cards left out of the 52, and simplify that down. Or you could do a full-on complement using the complement formula. You could actually go 1 minus the 4 out of 52 that I don't want, and you end up with the exact same answer. Different ways of thinking about things ends up with the same result. Not a red queen. So just the red queens. Do you guys need the diagram, or are you pretty familiar with cards now? Pretty familiar with the cards? So there is 2 red queens out of the whole 52 cards. So that means that there is 50 out of the 52 that are not a red queen. Again, you could do a complement here if you wanted to. And that simplifies, you can divide top and bottom by 2 to get to 25 out of 26. H, a red card or a club. So there's 26 red cards, and then there's 13 clubs, which means that altogether there is 39 cards that are either red or a club. Remember to look out for those little words and an or. So this is or, it can be either. And that, understandably, is 3 out of 4 of the suits. So 3/4. Okay, pretty straightforward, I hope, right? Okay, question 2. A card is drawn at random from our pack of playing cards. Find the probability that it is not a club. So let's practice our complement here. So 1 minus, if we don't want clubs, there is 13 out of 52 clubs. And that makes 3 out of 4, 3/4 of that deck that is not a club. Find the probability that it is not an even number. So we did work out already in part 1, the probability of an even number was 5 out of 13. So since we've already got that, if we want the probability that it's not an even number, we would just do 1 minus 5 out of 13, which is 8 out of 13. Find the probability that it is not a red 7 nor a black queen. So we're going to work on the complement here. I'm going to subtract off the parts that I don't want. So starting with 1, I don't want a red 7. There is 2 red 7s, so let's subtract 2 out of 52 for the red 7s. And we don't want a black queen, and there's 2 of those. So subtract another 2 out of 52 for the black queens. And that makes 12 out of 13. Question 3. A drawing pin was thrown 400 times and fell point up 362 times. So you know a drawing pin, those little metal things that have like the little dish on one side, like little thumbtack things you stick in the wall? I'm pretty sure that's what they're talking about here. So when you throw them, most of the time, the point faces down, which is out of the 400 times, it was 362 times that it fell point down. And the rest of the time, that was point up, and the rest of the times it was point down. Yeah, because the big dish, it would make sense that it does land with the base down. All right, so part A. What were the relative frequencies of the drawing pin falling point up and falling point down? Relative frequency is really the same as finding a probability. Okay, so let's look at, there's 2 scenarios that we want here. we want the relative frequency of point up. Okay, so point up was 362 times out of the 400. Okay, that will simplify to be 181 out of 200. Now, most of the time with probability, we prefer to leave our answers as fractions unless it's otherwise stated in the question. So you want percentages or you want a decimal. It is interesting though that is 0.905, which is definitely the majority when you see that as a decimal. The relative frequency of point down, if you do 400 minus that 362, that means that there is 38 times that it landed point down out of the 400, which simplifies to 19 out of 200, which is a 0.095 as a decimal. What probability does this experiment suggest for the result of point up? So in a way, we're repeating ourselves a little bit here. I was already indicated that the relative frequency is pretty much the same as probability, so it's trying to make that connection here. So the relative frequency of point up is the same as our probability of point up, which is 0.905. However, when we're referring to a probability, that has been measured down to the thousandth, right? Because we've got tenths, hundreds, thousands, remember your place values? Is it a reasonable conclusion that our probability has been measured down to thousandths when we've only done 400 trials? Okay, so that's the kind of thing that it's saying there. What is the probability does this suggest for a point up? And a little bit of a discussion there that with only 400 trials that we can't really be confident in that third decimal place. We would need to do more trials to really have it to that kind of accuracy. So I'm going to write a little statement in there. So, but with only 400 trials, we cannot be confident with the third decimal place. Therefore, it would be safer, or would be safe, to say that the probability of point up is approximately equal to 0.9. Because if you go, the probability of 0.9 is 0.905. That sounds super duper accurate, which we haven't actually done enough trials to be that accurate. Whereas we say it's going to be approximately 0.9, that is a lot more of a reasonable thing to say. It's that first decimal place. All right, a machine later repeated the experiment 1 million times, and the pin fell point up 916,203 times. Does this change your estimate in part B? So first of all, let's work out our new probability based on this experiment. The probability of point up is 916,203 over 1 million. Now, we kind of need to see that as a decimal. That is approximately equal to 0.916. Okay, so our estimate is in the right ballpark, but if anything, our estimate was just a little bit on the low side. Okay, so it just does ask us to make a little bit of a statement there. So this suggests that our estimate in part B was too low. More trials always gives you a more accurate result, doesn't it? Okay, so that's what we're doing today, 12A. Hopefully those questions will be just as quick as the ones that we've just done.